Okay, so see, if you get a square section, regular square section, the solution is similar to a rectangular section beam. The only difference in that will be the moment of inertia of the section. It is BD cube by 12 for rectangle. Since for a square, B and D both will be equal, so it becomes B raised to 4 by 12. That is the only difference. In this numerical, what he has said is the square section is used with one diagonal horizontal. So we just draw the square section, right? So this is my square section. These are the diagonals, and he's saying this diagonal, one of the diagonal is horizontal, so the other diagonal will be vertical. So it is tilted like this. So the solution is completely different. Let us try to solve this. Now what I will do is, yesterday we discussed about triangular cross section, correct? So here I am assuming this to be two triangles, right? Two isosceles triangles which are adjacent to each other with their bases, common base, right? So that is how I am going to solve this. Now by symmetry, I can say that the location of center of gravity is here, right? And this will be my neutral axis. Okay, this is my neutral axis. This is the other diagonal. So let me just name that as N A. Okay, this is neutral axis. Now I'll just name this square section. I'll start from here, A, or I'll start here, A, B, let this be C, and this will be D. Okay, and what he has given is the diagonal. This diagonal is given as 100 mm, right? So this diagonal length is 100 mm. Obviously, the other diagonal will also be 100 mm. Uh, now I'll make a construction in this. What is the construction? I will draw a line parallel to AC, and I'll call this as E and F. Okay, so this is the similar construction we had done yesterday for the triangle. Now I will find the shear stress at this level in the cross section, right? And based on that we can calculate, I'll actually derive an equation for this, and then we will calculate the maximum shear stress and shear stress at other locations. Okay, now let us start. um, Now the shear stress at this level is given by, just copy this equation from here so that I don't have to type. Right? Shear stress at any section is given by this equation. Now I have considered a section or a layer EF, and this is at a distance y from the apex. Okay, I will call this length as y. And the location of center of gravity from the apex just take this further. Right, this is y star, and this is equal to 100 by 2 or 50 millimeters. Since it is symmetric, so we don't have to worry much about finding the values. Okay, now let us go back here. I have to first find this a y bar at EF. It is similar to this numerical what we did yesterday. So I will just copy the same thing, right? Or we will do it again because if anyone has missed it. So AY bar is equal to, it is area moment, right? Now area of this triangle BEF, right? So it is half into base is EF into height is Y, right? So this is equal to I will sorry, this is the area, this multiplied by the distance from the center of gravity of triangle BEF and the neutral axis NA here, right? So how do you take this? I'll put a bracket here into it is y star minus the location of center of gravity of this triangle is at 1 by 3 from the base, that is EF, or from the apex it is 2 by 3 y. So minus 2 y by 3. Okay, so this will give me AY bar. Now I have to find this EF. Now in this triangle we have done all these things yesterday. This ABC and EBF, right? So these two are similar triangles. So I can write EF by AC is equal to Y star, that is this height BG by Y. So from that, or I'll just write it down here only. So I need EF. So EF by AC is equal to Y by Y star, right? Or EF is equal to Y into this AC is actually the diagonal, so I'll call this as uh, B, right? Width B uh, divided by Y star. I need to derive an expression, so for this reason I'll just keep it like this. So EF is equal to B into Y by Y star. By y star bar. Okay, so this is the value of EF, right? Now B is actually 2 times Y star, correct? This is Y star, this is B, and this is also B. So I'll just substitute that value here. So this is equal to B is 2Y star, right? Now this Y star gets cancelled, so EF will be equal to 2Y. Okay, so I got the value of EF. Now I can substitute in this expression and try to simplify. And I know the value of Y star, so I can put that value also and try to simplify this. So now let me just copy this again. A Y bar is equal to half into EF. EF is 2Y into Y star is 100, right, minus 2Y by 3, correct? Sorry, Y star is 50, not 100, it is 50, or I'll just put it as B by 2, that is better, because I need to derive a generic expression for this. Now this 2 and 2 gets cancelled, so here I have Y square, and this is B by 2 minus 2Y by 3, right? I'll just simplify this further. Y square, why it is coming like this, Y square into this will remain as it is, right? So AY bar became Y square into B by 2 minus 2 by 3 Y. Now I have to find the moment of inertia. This is over. B is, we know that already, right? B is the diagonal, so I'll keep that as it is. And I need moment of inertia now. So moment of inertia of whole section about neutral axis. So let us go to the diagram. See, this section is actually two triangles, right? So I have to find the moment of inertia of this triangle about the base and multiply it by 2. That will be the moment of inertia of the complete section, right? So I NA is equal to 2 times I or moment of inertia of triangle ABC about its base, right? So 2 times moment of inertia of the triangle ABC about its base. Now, what is this? This is the moment of inertia of the triangle about its base is given by base multiplied by, right? So this is the base, so I have taken that as B, and this is the height, right? So height will be in this case b by 2. I'll again put that in the bracket, b by 2 uh, whole cube, right? And this entire thing, just cut it again, b into d by 2 or bd cube by 12, right? So this is the moment of inertia of a triangle about its base. This is base, this is height. Base into height, cube of height divided by 2, 12. And there are two triangles, so I am multiplying this by 2. Now this b and this b cube, it becomes I'll take the ratio like this. So I have 2 here. So 2 into b into b cube. So it becomes b raised to 4. This 2 goes down and gets multiplied by 12. Or I can just cancel these two, right? So if these two gets cancelled, sorry. There is 2 here. So 2 into 2, 4. 4 into 2 is 8. So 8 goes to the denominator. So 12 into 8. So what is this? 12 into 8 by 2 is 48. So this will be b raised to 4 by 48. So this is my moment of inertia, and b in this expression here is 2y, right? So which we already have. So I can substitute the values in this expression and find the shear stress. Now shear stress at EF, tau is equal to F by I AY bar by B. Now what is AY bar? AY bar is this value, y square b by 2 minus 2y by 3. So I am just substituting that value there. What is b? B is 2y. We have here EF is 2y, and I is b raised to 4 by 48. So b raised to 4 by 48, right? Now we have to simplify this. So this is equal to, this 48 goes to the numerator. So 48 F by b raised to 4. I don't know why there is a line there, right? Into this y and this y gets cancelled. So what remains there is just one y, right? Now this b is also 2y, right? I will substitute, no, actually this b is the width of the section, right? So I'll keep that as it is. Now these two are having different bases, so I'll just cross multiply this. So when I cross multiply, uh, this denominator will be 6, right? So it will become 3b minus 2 into 2, 4y. So this into 3b minus 4y. In the denominator now I have only 2 here. 2 into 6. So that will become 12. Right? So this is what we get. Now this 12 and 48 gets cancelled, and I get 4f by b raised to 4 into this. So this y I will take it inside. So it becomes 3by minus 4y square. Okay, I'll take this in the next line, or tau is equal to 4f by b raised to 4 minus 3by minus 4y square by 12. Right? So using this equation, I'll call this equation as 1. Right? I can find the shear stress at
Cancel,
any.
no, sir.
Sorry.
The 12 get cancelled to 48, no, sir.
Oh yeah, yeah. Correct. Just this. Correct. So now this equation gives me the shear stress at any section between apex B and this diagonal AC. Right? You just put the value of y in this expression, you will get the shear stress. Right? Now what I have to do is I need to find the location and magnitude of the maximum shear stress. Right? So for maximum shear stress, we have um, d by dy of, or I'll write like this, d tau by dy is equal to 0, right? Or d by dy of this expression, right? And this should be equal to 0. Now let us differentiate this. So when you differentiate this, this is a constant, right? It will remain as it is, or you'll get 4f by b raised to 4. This is y, so the differentiation of y will be 1. So 3b minus 4y square. So y square will be 2y. So 2 into 4, it becomes 8y. And this is equal to 0. Or 3b minus 8y is equal to 0, or y is equal to 3b goes on the other side, 3b by 8, or 3 by 8, right? Now B by 8 into B is 100 mm, so it is 300 by 8, 37.5, right? So when the value of y is 37.5 mm, we will have the maximum shear stress. So let us calculate the maximum shear stress, or from this expression I'll try to find the shear stress at various points. First B and D, right? If you put y as 0, this will become 0 and this will become 0, so tau will be 0. So shear stress at B uh, is equal to 0, right? And at D also, at D y is equal to B, right? So this will become 3b square minus this will also be b square, right? Sorry, we'll not go till there. It is only till this point because this is applicable till the neutral axis. So again, here when you start from this side, here also you will get 0. At D, directly say B and D, it will be 0. Then shear stress at neutral axis, right? Y is equal to B by 2, which is equal to 100 by 2, 50 mm. So in this expression, you put the value of y as 50 millimeter. So let us use this. Tau is equal to 4f. What is f here? F is 200 kilonewton. So in 200,000 kilonewton, and B is 100 mm, so 100 raised to 4. Again here B is 100, Y will be 50, and this Y is also 50, right? So this is equal to, now let us calculate this. So 200,000 into 4 into 3 into, sorry, 4 into 200,000 by 100 raised to 4 is this much, into, open the bracket, this is 3 into 100 into 50 minus 4 into 50 square. So this is 40 megapascal, right? So this is at neutral axis. Now maximum shear stress, I'll copy the same formula. Uh, Maximum shear stress is tau max. This will remain same, 3b Y value will be 37.5, and here also it is 37.5. That is equal to, let us calculate this, 200,000 into 4 by 100 raised to 4 is this, into 3 into 100 into 37.5 minus 4 into 37.5 square. So it is 45 megapascal. Okay, so I have, at all the salient points, I have the shear stress. Now 37.5, let me project all these values now. 37, this is 50, BG is 50, so 37.5 is somewhere here. Okay, and here also we will have a similar point. And here it is 40. Okay, so the shear stress distribution will be something like this. Uh, yes. Right, so the maximum shear stress is at these two locations, and at neutral axis it is 40. Right, so just you can write down the values here. Oops, I should have projected it here. Mhm. This carries marks in your exam, so please try to at least draw it a bit neatly. Right, so this is the shear stress distribution. You just write the value 0, this is 45, here it is 40, again 45, and this is 0. Right, so this is the solution to the given